In this episode, a super-sized sub.
To come down the waterfront, to see these submarines being built, it is truly a magical thing.
Pushing marine engineering to its limits.
The Virginia class is acoustically the stealthiest submarine that the U.S. Navy has ever produced.
And the pioneering historic innovations.
This is a nuclear reactor.
The teardrop hull form became the standard for all modern submarines.
That made the impossible possible. For much of its history, the submarine has been a deep-water deterrent. But as the face of combat changed during the 1990s, the US fleet was in need of an update.
The Navy was looking to the replacement for the 688 class ships. They were nearing the end of their useful life. Similar to a vehicle, it gets wear and tear over time, and it was time to come up with the newer model.
And what designers came up with would break the mold of maritime engineering.
What we're looking at is the 15th Virginia-class submarine, the USS Colorado. She's 377 feet long. She can dive to depths greater than 800 feet. She can operate at speeds greater than 25 knots.
The Virginia class is one of the most advanced nuclear-powered fast-attack submarines ever produced for the US Navy. At the Electric Boat Shipyard in Groton, Connecticut, the 15th vessel of the class is currently being fitted out. For company Vice President Ken Blomstead, it still poses a huge engineering challenge.
And starting with the first ship of the class, it took 15 million hours to build that ship. And with the Colorado, we brought that cost down to 10 million hours. That's the kind of effort that's required to put one of these remarkable ships to sea.
And for the commander of the completed sister ship, the USS Missouri, Fraser Hudson, this trailblazing class is incomparable.
I've served on 3 classes of submarines, and by far the Virginia class is the best engineered that I've had the pleasure of serving on.
First launched in 2003, this technological titan is as long as 26 family cars and weighs in at 7,800 tons, equivalent to 40 blue whales. Equipped with an advanced nuclear reactor, it can dive up to 240 meters, but is also capable of inching across the shallows with pinpoint accuracy, courtesy of a control room equipped with a cutting-edge automated navigation system.
The pilot can literally dial in any depth, any speed. It allows the ship to operate in much shallower water close to shore. The combination of stealth, endurance, the versatility, the range is truly a benchmark for all ships.
In creating this super flexible maritime marvel, the Virginia-class designers have had to overcome several seemingly impossible challenges. Man has endeavored to operate underwater for centuries. Ancient sponge divers would plummet to the seabed with the aid of a weighty rock, holding their breath for minutes on end to retrieve their precious bounty. In the 5th century BC, Greek diver Silas was able to breathe underwater using a hollow reed. while sabotaging the enemy Persian fleet. Legend has it, Alexander the Great made the first mission in a submersible craft. Lowered into the Bosphorus Straits in a clear glass barrel, it's thought he spied on enemy sea defences. Being able to actually control a vessel in the underwater world was even less straightforward, and thousands of years on remains a huge challenge. Today, at the 1 kilometre-long David Taylor Model Basin facility in Maryland, budding nautical designers are striving to master submersible design at the annual International Submarine Races.
Scores of young engineers from around the world have brought submarines that they've designed and built with the goal of becoming the fastest human-powered submarine. The challenge is go 100 yards without coming out of the water, touching the bottom, touching the sides, or any part of the submarine falling off.
It may not be a huge distance, but the fundamental task of remaining submerged is no mean feat.
So up and down is a little bit difficult. Left and right so far has been really good. I can follow the line. It's just been a question of keeping the buoyancy right.
Did we make it further than before?
We got about, sort of halfway. The trim is slightly off. Like the controls seem to be working, the propeller's definitely working.
The secret to successful submersibles may still challenge some of the finest young engineering minds. But a huge breakthrough in submarine development was made possible 240 years ago, courtesy of American inventor David Bushnell. Dr. Rhys Morgan is at the Royal Navy Submarine Museum in Gosport, England, to find out about a secret weapon from the American War of Independence.
And this is it, the Turtle, the first submersible used in recorded underwater combat. Bushnell's plan for the Turtle was to sneak up on the British enemy ships moored in New York Harbor. The vessel had lots of weights in it to help it sink into the water, and underneath the base there was a ballast tank which would be filled with water. And the operator, a man called Ezra Lee, would pump the water in and out of the tank to help sink to the right depth.
As the Turtle slipped underwater, its two surface-mounted snorkels would become sealed, leaving the pilot with a limited air supply, as he powered the craft using his ingenious hand-cranked front-mounted propeller. As he approached his target, his mode of attack was even quirkier.
The Turtle's weapon, a keg of gunpowder, was attached to the back of the wooden hull. As the submarine silently crept up underwater to the base of the ships, it would be attached by this drill, which would be literally hand-drilled into the base of the ship.
Unfortunately, the pilot Ezra Lee hadn't banked on the British fleet being equipped with a metal hull.
By sheer bad luck, Ezra Lee wasn't able to drill into the ship's hull, so the Turtle was a bit of a failure. But having said that, it did set the precedent for submersible combat, and the principles of ballast tanks and propulsion still to this day remain on all submarines.
Unlike the one-man Turtle, the Virginia class can hold up to 135 crew. As ship's manager Patty McDaniel fits out the class's latest vessel, conditions are less cramped than on board its historic predecessor, but still tight, and ingenuity is called for.
One of the challenges with the design of the Virginia-class ships is all of the services and equipment that we need to fit into a tight space. So all through construction, we try to design having spaces to put all of the services up in. One of the other challenges with that is the crew when they come out to sea. These racks are the extent of the space many of the crew members have to store all of their items. So just this thickness deep is what these sailors have to have all of their clothing and books and whatever they choose to take out to sea with them.
And this compact theme continues on board, whatever the rank.
This is the wardroom of the Virginia-class submarine. So the wardroom, as you might imagine, is where the officers gather to eat. Among other things, it's also where a lot of the meetings happen to discuss all of the ongoings on board the ship. Interestingly, too, submarines are very limited on space, so the table is a large, clear surface, so this doubles out at sea as if you needed to have an operating table.
When these super subs are in service, they can dive significantly deeper than the hand-pumped submersible Turtle. Their ability to reach depths of 240 meters is down to a sophisticated system of internal and external ballast tanks, capable of holding gallons of water.
We have 5 external ballast tanks that are normally filled with air when I'm riding on the surface. When it is time for us to dive, we'll open vents on those ballast tanks. There's grates on the bottom of the ship that allow water to come in, displace the air, making the ship just slightly negatively buoyant. We then proceed down to the depth that we want to go to. And we use internal ballast tanks to make the ship neutrally buoyant, but then we can progress on our way whatever depth we choose.
Faced with a variety of missions, the crew on board the Virginia-class have an abundance of cutting-edge controls, one of which has replaced the most iconic feature in submarine history. The periscope has been the sub's eye to the world since the late 19th century, but engineers have taken the bold step to substitute it for a state-of-the-art photonic mast.
The photonic system is a mast with a sophisticated camera system that allows what would normally be displayed just in a periscope to be displayed on widescreen monitors throughout the ship.
I used to have an optical periscope that came down, which drove the construction of the submarine and the orientation of all of the rooms on the submarine.
Traditionally, the bulky structure of the periscope forced the control room into a cramped upper deck. But on the Virginia-class, the compact imaging equipment is only housed in the part of the structure known as the sail, allowing the sub's nerve center to be located on the wider second deck.
My control room that I'm standing in right now houses all of the important decision makers. It really brings the crew together to operate as a team, as a unit.
The Virginia-class designers are pushing nautical boundaries. But to make their mark in maritime history, they face more challenges and have to draw on innovations from the past.
Wow, look at it. Look how smooth the flow is off the stern as it passes through that dive field.
To produce more impossible engineering. The $2.7 billion Virginia-class submarine is the US Navy's most advanced attack sub. The 15th vessel of the class is currently under construction at Groton, Connecticut, and ship's manager Patty McDaniel is in no doubt about its engineering pedigree.
What we have now on Colorado really incorporates the latest and greatest of what's out in industry. We're always improving, we're always getting better, and we'll continue to evolve.
I really believe Virginia-class submarine has set a benchmark for marine engineering. The designing and building the Virginia-class was a continuation of all the great work we've done for over a century.
Unlike many of its historical predecessors, the 115-metre-long streamlined sub is built for a wide range of missions, including reconnaissance and surveillance. A sophisticated system of sonar arrays allow it to map its way across the ocean floor, propelled by a virtually silent advanced propeller known as a propulsor.
The ability to put literally tens of thousands of horsepower into the main engines, into the propeller, and yet be so quiet. The level of technology required to do that is amazing.
Warship bearing 054, range 1,000 yards.
The Virginia class is acoustically the stealthiest submarine that the U.S. Navy has ever produced.
But as well as remaining undetected in the world's oceans, the submarine's flexible remit also calls for speed and maneuverability. So how do you construct a streamlined hull capable of cutting through the world's oceans? To achieve this, the Virginia-class engineers looked to one of history's greatest nautical innovators. Until the end of World War II, submarines were essentially surface ships with the ability to dive for a maximum of 48 hours. Underwater, the vessel became relatively cumbersome and inefficient. To improve performance would need a total rethink in submarine design. Naval engineering professor Matt Werner has come to the Webb Institute of Naval Technology to see firsthand how engineers came up with a solution.
So here we have our World War II submarine. And if we compare it to this model of a surface ship, we see a great number of similarities. This hull form is really about traveling on the surface.
Its sleek design creates an extremely low bow wave, resulting in a small wake and low resistance, all perfect for minimizing drag on top of the water.
When we take the same hull form and place it below the water, we pay a penalty for this type of hull shape.
Surface-mounted equipment and an uneven hull shape create both frictional drag between hull and water and form drag, as water separating from the hull causes resistance-inducing eddies, dramatically reducing speed. To create a submarine that was more efficient beneath the waves was a design conundrum. The solution would be down to charismatic Admiral Charles Mompson. The US naval officer would commission over 25 large-scale models with the sole intention of creating speed and performance underwater. Finally, all of his testing paid off.
Those models ultimately resulted in the teardrop hull form that became the standard for all modern submarines.
To appreciate this game-changing design in motion, Matt is injecting dye into the tank to analyze its hydrodynamic qualities.
So we've got the model in the water now. We're towing it below the surface. We put dye in front of it, and the model will pass through that dye field. And hopefully what we'll be able to see is some nice smooth flow across the stern of the model as it passes by. So let's see how it goes. Okay, so it's coming into the window now and right into the dye field. And the bow goes through the dye. And wow, look at it. Look how smooth the flow is off the stern as it passes through that dye field. That's showing me we have very low resistance.
With an even, rounded, streamlined shape, the teardrop hull dramatically reduces both frictional and form drag. And in 1953, the culmination of this groundbreaking work was an engineering masterpiece.
So after countless hours, tests, and calculations, Admiral Munson and his team had done it, and this is the result. The USS Albacore.
The revolutionary albacore changed the face of submarine design.
By getting away from that ship-type hull form and going to a true submerged-type hull form, we have the fastest thing in the water, the most maneuverable sub ever to that point, and the baseline for all subs to come.
Over 60 years after the albacore first set sail, the US Navy's Virginia class still adopts Admiral Momsen's game-changing teardrop hull.
We need to have very strict circularity requirements to ensure the hull sections are very circular. And when we join them together to form the pressure hull, they must be extremely straight so that our travel through the water uses the minimum amount of energy.
At the Rhode Island Manufacturing Center, modern construction techniques have taken hydrodynamics to an unprecedented level.
We have 3,600 dedicated men and women who take raw steel plate, pipe, and cable and create completed 2,000-ton modules. Raw steel plate is brought in, cut machines automatically cut the plate to the right dimensions. In the case of pressure hull structure, it's rolled to get that circular shape for the pressure hull.
It takes 5,000 tons of force to form the robust steel into the iconic submarine shape. Engineers then adopt a sideways approach to fitting out.
Hull cylinders are turned axis vertical and outfitted with structural shapes like internal tanks and large piping assemblies. It allows us to use cranes and vertical picks to drop those assemblies in and more cost efficiently install them.
Each of the cylinders are then placed horizontally, allowing outfitted decks to be slid in. Before the completed modules are shipped off in preparation for final assembly. A process that never fails to impress ship manager Patty McDaniel.
When you pair up the last hull section and you actually have the ship look like a whole ship together in a bay, it's really exciting to see it all come together.
And transporting this monumental structure to its natural habitat is no less impressive.
We actually have 78 of these transfer cars moving in unison. It's one individual flipping one switch and all of the cars start moving together. And it drives the whole ship out along the tracks on the floor, right out to the pontoon, and we float off.
This giant of the deep is taking engineering into uncharted territory. But to create one of the most advanced submarines in history, its designers need more inspiration from the past.
This is an incredible moment. What an amazing feat of engineering.
To produce more impossible engineering. The US Navy's Virginia class is pushing the boundaries of submarine design. Program Vice President Ken Blomstead has been at the heart of its engineering since 1996.
When I saw the original requirements for the Virginia class, there were several requirements that I thought were pretty challenging. But as we started to build the ship, it really came together and turned into just a great platform.
"115 meters in length, each sub is made up of just 4 supersized modules, but contains around 1 million components and requires 10 million man-hours to build. Engineering on this epic scale is an awe-inspiring experience for ship's manager Patty McDaniel.
It's really been amazing seeing these systems that I did the calculations on be built and tested and then actually eventually go out on sea trials. It's really a privilege to be able to see it all come together.
For the crews on board, a key to the success of each mission is the ability to stay underwater for prolonged periods of time.
This crew of 135 sailors have to be able to go anywhere in the world, deploy from their home port, and be operating in any ocean and not be concerned about the amount of fuel consumption that they're using.
So how do you propel a submarine to the most remote parts of the globe without having to refuel? This seemingly inconceivable task would not be possible without another innovation of the past. Early submersibles relied entirely on human power for propulsion. In 1620, there are accounts that Dutch engineer Cornelius Drebbel
down we go.
submerged a fully crewed vessel into the River Thames and then rowed it from Westminster to Greenwich.
And stroke.
Although historians now believe a semi-submerged tidal drift may be a more accurate version of events.
Useless.
In 1863, the first mechanical submarine was launched, running on compressed air. The Plongeur had an impressive top speed of 4 knots,
Ooh la la.
but had to be incredibly long to house its 23 air tanks, and needed a support ship to top up supplies.
Ow! Watch it!
Cracking the huge problem of submarine propulsion would be down to one of the most colossal scientific discoveries of all time. Dr. Rhys Morgan is at a secret decommissioned location in Austria to discover more.
This is a nuclear reactor, the core of a nuclear power plant. The core itself is a whopping 20 meters deep. If up and running, this reactor alone would produce enough electricity for 1.8 million homes. This is an incredible moment. What an amazing feat of engineering.
The world's first peacetime use of nuclear power occurred when the US government switched on the experimental breeder reactor in Idaho in 1951. It temporarily powered the town of Arco and paved the way for domestic nuclear power. But Captain Hyman Rickover of the United States Navy had other ideas. He recognized the potential for harnessing this power and using it in a submarine.
Rickover was an incredible pioneer. The problem with powering submarines is that most forms of power for propulsion require air, so the submarines had to resurface. Or the alternative would be battery, but they just didn't last.
Despite flying in the face of popular belief, Rickover was convinced that the fundamental process of a nuclear reaction to boil water and create steam could provide a groundbreaking solution.
Nuclear reactors are just very large ways of boiling water. And here I've got a steam cleaner that's going to represent my nuclear reactor. I've got some water, and when I pull the trigger, it boils the water, turning it into steam. As I direct the steam towards my turbine, it starts to generate electricity, and that turns on my light. The difference between my little reactor here and this enormous one here is in the way that the water is heated. And the answer lies at the very heart of the core itself. Nuclear fuel rods contain thousands of uranium pellets, and it's the uranium atoms that split causing a chain reaction that generates vast amounts of energy in the form of heat. The result is an almost limitless supply of power that can keep on producing for years. The problem Rickover faced was scaling down something as huge as a nuclear reactor down to the size of something that could fit into a submarine and still provide the power.
Rickover's solution was the world's first pressurized water reactor. The core inside his super-efficient reactor vessel heated a loop of pressurized water. This in turn vaporized water in a secondary loop, creating steam to drive the main turbine, producing electricity. After vigorous testing, in 1954, Captain Rickover watched as the Nautilus was launched. A pioneering nuclear vessel that would travel 1,300 miles in less than 90 hours, fully submerged.
This was a huge game changer in submarine engineering. Previously, submarines could only stay underwater for up to 48 hours. Now there was absolutely no need to resurface. Rickover and his incredible engineers had made the impossible possible.
The pioneering Nautilus's reactor only had to be refueled every 2 years. But the Virginia class has taken this pioneering technology to an unimaginable level.
The Virginia-class submarine has a life-of-ship core. It never needs to be refueled. Previous submarines had to be refueled during its life.
The Virginia-class submarine is powered by a nuclear reactor that has been designed to last the life of the ship for all 33 years.
Converting seawater to steam, this top-secret reactor plant is capable of powering the vessel for over 1.5 million kilometers without refueling, as well as generating all the electricity on board the sub.
The ship has amazing capabilities. In fact, the only limiting factor for me when I go to sea is the amount of food that I can bring on board. The nuclear power provides us the ability to operate anywhere in the world, in any ocean environment.
And astonishingly, its unlimited power source also allows the vessel to hover motionless in one location for weeks at a time.
The reactor on the Virginia class is the most advanced reactor that the U.S. Navy has produced.
But sustaining over 130 crew underwater in a sealed vessel for months at a time requires yet more inventions from the past.
We're about 5 minutes in now. We're really starting to use up the oxygen
to create this impossible engineering. For over 2 decades, an army of designers, engineers and workers have been creating the Virginia class, one of the most sophisticated subs ever built for the US Navy.
It is wonderful to wake up every day, to come to work. Everyone takes a lot of pride in what we do, and it's a joy to see it come together.
12 super subs are now in service, each equipped with a state-of-the-art nuclear reactor that allows the vessels to remain underwater for months at a time. But keeping the crew safe for these prolonged periods, as much as 240 meters below the surface, poses a huge challenge.
In the submarine, we have an enclosed environment, and so we have to monitor the atmospheric controls on board and the levels of the oxygen, the carbon dioxide, and other trace gases to make sure that it remains habitable for the sailors.
So how do you keep over 100 crewmen alive for months at a time? The answer lies with the work of a genius chemist over 200 years previously. To appreciate the problems of creating a human habitat underwater, Dr. Rhys Morgan is being put through his paces at a naval test facility in Portsmouth, England.
This is a hyperbaric trials unit used by navies around the world to test undersea and high-pressure systems. This HTU can uniquely recreate the kind of immense pressures experienced by submarines at the very bottoms of the ocean.
Rhys is using this technology to put himself in the shoes of the early submariners, to experience just how quickly the atmosphere on board could change.
This is a potentially dangerous experiment, so I'm here with Jules, who's going to look after me inside the chamber. Outside, there's a whole team of medics looking after both of us. This is a completely sealed unit now.
Rhys and his crew now replicate the physically demanding work on board an operational submarine.
It's amazing how you do start to feel slightly more out of breath than if you were just outside on a normal exercise bike.
CO2 makes up just 0.04% of our normal atmosphere, and in this quantity is completely harmless. But in a sealed unit, the level builds as we exhale and can become dangerously toxic.
We're about 5 minutes in now, and we've already created half the maximum permissible CO2 levels in the chamber. So we're really starting to use up the oxygen. A bit hot. Okay.
After nearly 6 minutes in the chamber, the oxygen and CO2 levels have become completely unbalanced, and it's considered too dangerous to remain inside.
Exhausted. I don't know how those early submariners did it. I could really feel the oxygen content lowering and the carbon dioxide increasing in there.
Submarine engineers of the Second World War would tackle increased carbon dioxide levels by chemically scrubbing it. Large quantities of soda lime spread around the sub would react with and absorb the CO2 in the atmosphere. But by far the bigger challenge was how to replenish oxygen levels in a completely enclosed vessel. The answer lay as far back as the early 1800s, through the work of an English chemist, William Nicholson. Inspired by the invention of an electric battery, Nicholson had the idea of placing battery leads into water. In doing so, he produced a chemical reaction, what we now know to be electrolysis.
This is a simple demonstration of electrolysis. I first have my water for the electrolyzer. Okay.
2 water-filled test tubes are placed over the submerged negative and positive electrodes before the electrical current is switched on.
And you can start to see immediately the gas bubbles forming on the electrodes here. The negative electrode is generating hydrogen and the positive electrode is generating oxygen. And so each of these jars now has displaced the water with the gas.
This reaction is caused by the positive and negative electrodes attracting and separating the oxygen and hydrogen molecules in the water.
Now what we're going to do is test the purity of the gas. And this jar here has got oxygen in. And if I blow this splint out, with the pure oxygen inside, it should glow. So there we have it. We've produced, in just a few seconds, enough oxygen to fill this test tube. What we need to do in a submarine is to scale up this whole process to provide enough oxygen for all the submariners deep beneath the waves.
The engineers of the Virginia class have built on this groundbreaking work to provide life-sustaining conditions under the water for months on end.
In order to maintain that environment without coming up for more air, we create oxygen through electrolysis. We have pure water. We then use electricity to split the hydrogen from the oxygen. We distribute the oxygen throughout the ship and then remove the hydrogen so that we can maintain levels right at 20%, just like normal air.
Located in the sub's auxiliary machine room, the US Navy's Advanced Integrated Low-Pressure Electrolyzer has a maximum capacity to create over 200 cubic feet of oxygen per hour. The potentially toxic carbon dioxide is removed by a sophisticated amine-based removal plant.
You expel carbon dioxide and that builds up in the ship. I have atmospheric control equipment on board that absorbs that carbon dioxide. I then compress it and can either store it or discharge that as well.
Although the crew on board experience normal living conditions, when working up to 240 meters below sea level, all-round safety is a huge consideration, and every eventuality has to be prepared for.
In the unlikely event of a submarine sinking, we definitely have the capability to escape.
In case a sub's internal atmosphere is ever compromised, Chief Warrant Officer Eric Nabors trains submariners to perform a pressurized escape in an ingenious piece of equipment known as a size suit.
It's designed to provide the occupant fresh breathing air through the compression and ascent phases. It provides 75 pounds of positive buoyancy in the water. It travels at 625 feet per minute through the water column.
Topside, request permission to fill and equalize.
You have permission to fill and equalize.
As the regulated lifting force of the suit propels the students safely through the 37-foot escape trainer, they must follow one golden rule.
The number one rule of submarine escape is never ever hold your breath. Because the escapee is breathing compressed gas at depth, and they travel through the water column, the pressure around them decreases. We are concerned with pulmonary overinflation syndrome.
This potentially fatal condition could lead to the rupture of air sacs within a crew member's lungs.
If a student were to hold their breath, that would occur. So we teach them to breathe normally or exhale the entire way to the surface.
Incredibly, in open water, these technological marvels can withstand up to 250 pounds of pressure per square inch.
These suits have been tested to depths up to 600 feet of seawater. The size suit itself is an incredible piece of engineering.
It's now more than a century since the first self-propelled submarines plunged into the depths of the oceans. Now, by drawing from the innovators of the past, adapting their ideas, upscaling them, and making trailblazing discoveries of their own, the engineers, designers, and workers constructing the Virginia class are making history.
come down the waterfront, to see these submarines being built, to see the crew starting to take over system by system as we turn it over to them and bring the ship to life. It is truly a magical thing.
The Missouri just returned from 6 months of operations, and if you could imagine driving your car for 6 months straight, 24 hours a day, is truly a testament to the engineers who designed it, the people who built it, and those 135 sailors who operate and maintain it on a day-to-day basis.
They've succeeded in making the impossible possible.